Hello, today I would like to present our work that got accepted to IJCNN recently. The work is about unequal covariance awareness for facial discriminant analysis and its variance in classification. So you can recall that the core idea of facial discriminant analysis is to seek a series of projections that maximize the ratio of the between and within cast scatter matrix. An example can be seen in the figure. Here we have the two cases and we would like to maximize mu1 minus mu2 square over sigma 1 square plus sigma 2 square. Throughout the years, there have been many variants to deal with different types of problem or data. For example, the work on generalization of linear discriminant analysis using LP norm has the key idea of using the LP norm instead of L2 norm and Stevie gradient to optimize the objective function. Another typical work can be span linear discriminant analysis with application to high-dimensional, low sample size data. And its key idea is to develop a method for automatically incorporating variable selection in facial discriminant analysis. However, none of those methods developed so far has used the fact that the assumption of equal covariance matrices in facial discriminant analysis is usually not valid in practical situations. So that is the main motivation of our work. So an example can be seen through this figure. Here we have two cases, case by 1 and case by 2. X1 bar is the mean of the first class and X2 bar is the mean of case by 2. And Y1 bar, Y2 bar is the corresponding means in the projected space. And here the violet line is the mean of Y1 bar and Y2 bar. That is also the line that decide the classification rule. So the traditional strategy in facial discriminant analysis is to assign the observations on the upper part of the violet line to cast by 1 and the remaining ones to cast by 2. In terms of formulations, we can say that I will classify a sample X to pi 1 if its projection Z has Z minus Y1 bar square is smaller or equal to Z minus Y bar 2 square. So we basically just compare the distance between Z and the cast means in the projected space. However, you can notice that the variation within the first cast is smaller than the variation within the second cast. Also, if you shift the violet line a little bit upper, then that may result in a better classification rule. So our strategy is we take into account the variance within the classes and we classify a sample X to pi 1 if its projection Z has Z minus Y1 bar square over S1 square is smaller or equal to Z minus Y bar 2 square over S2 square. Here S1 square, S2 square are the sample variance of pi 1 and pi 2 in the projected space respectively. For a more general case where we have multiple casts, then we can allocate the observation X to the K population if it satisfies inequality number 1. Here Sij is the sample variance of the I cast in the J projected space and R is the number of projections. So you can see that này yj minus mkj square over skj square is the distance between yj and the mean of the k-cast in the j projected space. And then we sum across all the projected space. That is like we sum according to j from 1 to r. To analyze the method theoretically, we first have some notations. Here we denote by a to the power of t, the transpose of a vector a. Xi bar is the mean of the I-cast, and x bar is the overall mean, and xij is the j observation from the I-cast, I from 1 to c and j from 1 to ni. We also review some classical methods. So the classification rule for quadratic discriminant analysis is to classify the observation x to the k-class if dk of x is the smallest among the di of x that is defined in equation 2. And for linear discriminant analysis, it classifies x to the k-class if dk of x is the smallest among the di of x that are defined in equation 3. And lastly, Fisher discriminant analysis assigns a sample x to the k population if dk of x is the smallest among the di of x that are defined in equation number 4. So we now have the first theoretical result, which reveal the implicit use of the covariant matrices. So let Vj be the j eigenvector of W inverse times B. Then Sij square, the symbol variance of the projections of the I-cast observations into the J space, will satisfy quantity number 5. That's Sij square is equal to Vj transpose times Si times Vj. Here B, W and Si are defined in equation 6, 7, 8, and we can recall that B is the between cast scatter matrix and W is the within cast scatter matrix and Si is the sample mean of the I-cast. So you can see that through the use of Sij square, we implicitly use the information from the sample mean of the I-cast Si without computing it directly. And then from that theorem, we also have the following corollary, which say that let x be an observation and yj equal to Vj transpose times x, where Vj is the j eigenvector of W inverse times B. And we suppose that we only select the first R non-zero eigenvectors of W inverse times B that are V1 to Vr for classification. Then we have the equality number 9. And this equality shows the relation between the quantities in the original space and the quantities in the projected spaces. And we have the following analysis of the number of parameters. So for a classification test with G-classes, if R eigenvalues are selected for classification, then our methods have R times G more parameters to estimate than Fisher discriminant analysis. However, this is a really a minuscule increment compared to switching from Fisher discriminant analysis to quadratic discriminant analysis, which will result in G minus 1 times B squared plus B more parameters. So for evaluation, we use k-focused validation with k equal to 5, and the error rate is basically the misclassification rate, and our codes are posted on the following repository. And the experiment results are shown in this table. This is the 5-fold cross-validation results using Fisher discriminant analysis. Unequal covariance aware Fisher discriminant analysis, which is the second column, and the last column is quadratic discriminant analysis. So you can see that most of the time, almost all of the time, you see FDA, which is our method, perform much better than the traditional Fisher discriminant analysis. And interestingly, sometimes it even outperforms quadratic discriminant analysis. This is possibly because quadratic discriminant analysis has more parameters to estimate, but the sample size is not large enough compared to the number of features. And you can notice that for the CAR dataset, quadratic discriminant analysis doesn't even produce the result, and the same thing happened for the GRASS dataset. We also try to apply our framework on shrinkage Fisher discriminant analysis, which is a variant of Fisher discriminant analysis where the sample covariance matrix are replaced with the corresponding covariance linkage estimate. So the results are solved in this table. The first column, the second column, is a shrinkage discriminant analysis, and the last column is the unequal covariance aware version of shrinkage discriminant analysis. And again, you can see that in most of the cases, our method perform far better than the original ones. And we also try to apply a framework to LDA-LD, which is a generation of Fisher discriminant analysis that uses an LB norm instead of L2 norm in both the numerator and the denominator of the objective function. And this is the result, and the bold one indicates the best performance. Here, the column in the middle is LDA-LP, and the last column is unequal covariance aware version. And you can see that again, our framework boosts the original method significantly in terms of classification results. So this is the end of the presentation. Thank you very much for your attention.